Hello, today I'm covering the basics of faulting and deformation within the Earth's crust. To understand what faulting is, we need to understand the forces involved within the Earth's crust. At a glance from our perspective at the Earth's surface, Earth seems static and homogeneous. However, the ground beneath our feet is constantly shifting, being pushed apart and pulled by forces within the Earth's crust, mantle, and core. One of the forces shaping the ground beneath our feet is the weight of the ground itself. This force is called lithostatic or overburden pressure. To understand this pressure, we'll take a point within the Earth's crust and see how it reacts to this force. The rock above this point is referred to as overburden. As we can see, this overburden is generating a downward force. This downward force is then blocked by resistance of the material underneath this point. These two forces press up and down on the material in both vertical planes, squeezing the material out to the sides. However, this squeezing effect is blocked by the resistance of the material on the sides pushing back inward. Pressure generated by the weight of the overburden is therefore counteracted by the resistance of the surrounding material, making it what's called a confining force, where the force presses in from all directions. The molecules within the rock are compacted closely together, raising the melting point of the rock, as these close, tight bonds take more thermal energy to break. The temperature of the Earth's crust increases with depth. This is due to a number of sources: heat left over from the formation of the Earth, the decay of radioactive elements within the Earth's interior, as well as other sources. This increase will lead to brittle materials behaving more ductile as they approach their melting point. This leads to a drop in the amount of stress energy a fault system can store, decreasing the strength of earthquakes with depth, with the exception of deep-focused earthquakes. However, it's important to keep in mind that the lithostatic pressure also increases with depth, raising the melting point of that material. To understand both brittle and ductile deformation, we need to use a graph called Young's modulus. This graph plots stress, the force over an area inside the object, against strain. Strain is a measure of deformation using a ratio of change of object's length over its original length. If the strain is positive, that means the object is undergoing lengthening, meaning it's undergoing extensional stress. If the strain is negative, it's undergoing compressional stress. At the surface, most rocks undergo brittle deformation, where they can withstand high amounts of stress with little to no strain deformation. Different materials can withstand different stress loads. Here we can see basalt rock withstands more stress than a weaker rock like talc before fracturing. This is important when looking at earthquakes, because the stress energy within a fault system is what transitions into heat energy and seismic waves when it fractures. However, this changes when a material is heated. As material approaches its melting point, it will behave in a much more ductile way. As stress is introduced to a ductile material, at first it will experience elastic deformation, deformation that isn't permanent. If the stress is removed from the object, it will spring back to its original length, meaning the strain is not permanent. This elastic behavior will continue until the material reaches its yield point. If the material experiences stress past its yield point, it will undergo plastic deformation. Any deformation in this strain zone is permanent, even if the stress is removed. This plastic deformation will continue till the material reaches its ultimate strength, the maximum amount of stress the material can resist. The material will then experience what is called bottling or necking at the centroid, where it is literally pulled apart in an extensional environment. Under compression, it will thicken at the centroid. Eventually, the material is stressed till it reaches its fracture point and breaks. In a fault system, this break results in movement in the fault blocks, as well as a release of thermal and seismic energy, resulting in an earthquake. The closer the material is to its melting point, the less stress it can resist, and the more strain deformation experienced, till it simply flows like a liquid when force is applied. Fundamentally, there are three kinds of fault system. Two kinds of dip fault that are formed through vertical movement within the fault system, and slip faults, which are formed under horizontal movement. We'll cover the dip faults first. Normal faulting occurs when a section of brittle rock is placed under extensional stress from opposing vector directions. Or these force vectors could be moving in the same direction but at different velocities, with a faster block traveling ahead of a slower one, leading to the rocky body with faster velocity pulling away from the slower section of rock. The differences in force vectors will place the rock under extensional stress as it's pulled apart. The stress energy will build up in the rock till the rock reaches its fracture point. point, or the friction within the rock face is overcome. This energy will be released in the form of movement, heat, and seismic waves. The easiest way to identify a normal fault is to place yourself on the lower side of the fault. Next, you need to identify the hanging and foot walls. To do this, you need to look at the dip of the fault face. This is the angle of the fault face. Then we need to either draw or imagine a vertical line running up from the base of the fault face. If this angle, the angle of the fault face, crosses the line, then we're looking at the hanging wall. However, in this diagram, we can see that the face is angled away from the line, so we're looking at the foot wall. This means the hanging wall is the block of crust that we're standing on, and it has been pulled down below the foot wall. Therefore, this is a normal fault undergoing extension. Due to normal faulting occurring in an extensional environment, the rock in this fault system tends to behave in a more ductile manner in a shallower depth. This is due to the extension of the head wall block, leading to thinning of the crust and an increase in thermal gradient. As the material insulating the heat flow from the mantle is thinned, the extensional movement also acts against the confining pressure of the overburden. This can lead to decompression, resulting in melting, as the melting point of the affected material drops due to the decrease in pressure. This drop in pressure in the crust can also lead to material from greater depth and therefore greater heat migrating up to the surface due to the pressure drop. Reverse faulting occurs when a section of brittle rock is placed under compressional stress. This could be from opposing force vectors, or these force vectors could be moving in the same direction but at different velocities, with one block moving faster than the other, leading to the rock with faster velocity crashing into the rock section with slower velocity that's traveling ahead of it. These opposing force vectors will lead to the accumulation of stress within the fault system, till the fault system overcomes the friction between the fault faces, or the rock that makes up the fault system breaks. Again, this will release heat, seismic energy, and move the fault blocks relative to one another. To identify a reverse fault, we can use the same method that we did on the previous one. As before, we stand on the lower fault block. Then we draw a vertical line up from the bottom of the fault face. This time, the fault is angled so it crosses the vertical line. So we are looking at the face of the hanging wall block. This means the hanging wall block has been pushed up onto the foot wall, meaning this is a reverse fault system and this sectional crust is experiencing compression. The compression in this fault system does not oppose the confining pressure generated by the overburden weight. Typically, most changes in ductility or melting in a compression system come from frictional heating at the face, meaning it happens very quickly during a seismic event. However, there are some ways decompressional heating and melting can occur in this compressional environment, but they fall outside the scope of this video. Now that we've covered the two kinds of vertical dip faults, we can move on to horizontal strike-slip faulting. Strike-slip faulting occurs when you have two brittle bodies moving at different velocities or in the same direction at different speeds, traveling in the horizontal plane. This creates stress that will build up between these two brittle bodies till the stress energy stored is enough to break the rock or overcome friction between the fault faces, leading to the rock fracturing or the fault faces slipping as they overcome friction, releasing heat, seismic energy, and moving the fault blocks. Decompressional melting and an increase in ductility can occur if the bodies moving past each other stretch the crust. The crust is thinned and heating occurs as a result. This also leads to a force acting against the confining effect of lithostatic pressure, leading to heating within the material and a decrease in its melting point, potentially. But most heat in the system is generated through friction between the fault faces. It's easy to determine if a fault is strike-slip, as a movement is horizontal, meaning the hanging and foot walls are level. To look for strike-slip faulting, the easiest way is to look for misalignment in structures like rivers, roads, cliffs, and sedimentary bedding. Now that we've looked at the three kinds of faults, here's a few more important details. It's common for faults not to follow purely horizontal or vertical movement. Faults that have both a dip and slip component of movement are called oblique slip faults. It's also important to look at the bigger picture when using faults to determine if an area of crust is under extension or compression. You might have a very localized compressive force creating a reverse fault in a small section of crust within a larger region that is experiencing expansive force, leading to most of the region being dominated with normal faulting and vice versa. You need to look at the fault system in the context of the region to actually understand what's happening within the crust. I hope you enjoyed my video on faulting, and thank you for watching.